What if everything you see around you, the stars, the planets, even the space between them, is just the surface of something far stranger, far deeper? Picture this: a single atom vibrating in the void, its behavior dictated by rules so bizarre they defy common sense. Now stretch that strangeness across the entire cosmos, where the fabric of space itself expands faster than light, carrying galaxies away like leaves on a river. This isn't science fiction. This is the frontier of modern physics, where quantum mechanics and cosmic expansion collide in ways that will make your head spin. We're about to journey through 35 surreal theories that tie the infinitesimally small to the unimaginably vast. Think of parallel universes branching off with every decision you make, or time folding back on itself like a looped ribbon. Imagine black holes acting as portals to other dimensions, or dark energy, the mysterious force driving the universe apart, being nothing more than the echo of quantum particles popping in and out of existence. These ideas aren't just wild guesses, they're the cutting edge of what science is grappling with right now, theories so profound they could rewrite the textbooks of tomorrow. But why should you care? Because this isn't just about equations scribbled on a chalkboard. Unraveling these mysteries could change everything: how we understand time, reality, even our place in the cosmos. It's about peering into the unknown and asking the biggest questions. Are we alone in the universe, or is every possibility playing out somewhere in the quantum multiverse? Is time a river flowing in one direction, or a tangled web of moments? Strap in, because by the end of this video, you won't just see the universe differently, you'll wonder if it's been seeing you all along. Einstein might have dismissed it as spooky, but quantum entanglement is very real and far weirder than even he imagined. Picture two particles born from the same event, forever linked no matter how far apart they drift. Change one and the other instantly responds, as if they're whispering secrets across the void. Now stretch that idea to cosmic scales. Imagine entangled black holes, their fates intertwined across billions of light years, or galaxies mysteriously synchronized like dancers in a universe-sized ballet. This isn't just poetic speculation. Some physicists argue entanglement could be woven into the fabric of space itself, acting as invisible threads holding reality together. Take dark energy, the enigmatic force accelerating the universe's expansion. What if it's not some exotic substance, but the collective effect of countless entangled particles? Each tiny quantum connection, when summed up across the cosmos, might generate a repulsive force strong enough to push galaxies apart. It's a radical idea that the universe's biggest mystery could spring from its smallest building blocks. And here's where it gets even stranger. If entanglement truly spans the cosmos, it could mean the universe isn't just expanding, it's stretching in a coordinated way, like a cosmic canvas being pulled taut by unseen hands. But how do we test something so vast? Scientists are already looking for clues in the cosmic microwave background, the afterglow of the Big Bang. Tiny irregularities in this ancient light might carry fingerprints of quantum entanglement on a universal scale. Others study black holes, theorizing their event horizons could act as entanglement amplifiers, bridging distant regions of spacetime. If proven, this would mean the universe isn't just a collection of isolated objects, it's a deeply interconnected web where the behavior of one particle can ripple across eternity. The implications are mind-bending. If entanglement binds the cosmos, it could rewrite our understanding of cause and effect. Events separated by unimaginable distances might influence each other instantaneously, defying our classical notions of time and space. It's a reminder that the universe, for all its vastness, might operate more like a single, intricate organism than a scattered collection of parts. And if that's true, it raises an even deeper question. Are we, too, entangled with the cosmos, subtly shaped by forces we're only beginning to comprehend? What if everything we perceive as reality, the swirling galaxies, the trees outside your window, even the sensation of touch, is nothing more than an illusion, a cosmic mirage painted onto the surface of the universe? This is the startling premise of the holographic principle, where our three-dimensional world might be nothing more than a shadow cast by information encoded on a distant two-dimensional boundary. Think of it like watching a movie on a flat screen. The depth, the movement, the drama all feel real, but they're just patterns of light projected from a flat surface. Now scale that up to the entire cosmos. Every supernova, every mountain range, every fleeting thought could be a hologram, a projection from the universe's outermost edge. Here's where physics gets dizzying. Black holes play a starring role in this theory. When matter falls into a black hole, it doesn't just vanish. It's believed to leave behind an imprint on the event horizon, the point of no return. That imprint contains all the information about what fell in, just like how a hologram stores a 3D image in a 2D medium. Now extend that idea to the entire universe. Some physicists argue that all the information defining our reality, every particle, every force, might be similarly encoded on a vast, unseen boundary at the edge of space and time. It's as if the universe is a cosmic hard drive, with the three-dimensional world we experience being just the projection of data stored on a two-dimensional surface. But how could we ever test such an outlandish idea? Surprisingly, there are clues hidden in the fabric of spacetime itself. The holographic principle predicts that space should have a granularity, a sort of pixelation at the smallest scales. Just like how a digital image breaks down into tiny squares when you zoom in far enough, spacetime might have a fundamental resolution limit. Experiments using ultra-precise gravitational wave detectors could one day reveal this underlying graininess, offering proof that reality isn't as smooth and continuous as it appears. The implications are staggering. If the holographic principle holds, it could mean that time and space aren't fundamental, they're emergent properties, illusions created by the way information is processed. This blurs the line between physics and computation, suggesting the universe might operate more like a simulation than a collection of objects. It also raises profound questions about free will. If every event is predetermined by information on a distant boundary, are our choices truly ours, or are we just reading from a script written at the edge of existence? Yet the most mind-bending possibility is this. If our reality is a hologram, then the true, real universe exists in a form we can't perceive, a higher dimensional space where the rules are utterly alien. It's a humbling thought that everything we know might be a shadow on the wall of a cosmic cave, a flickering image cast by something far beyond our comprehension. And if that's true, what else is out there, waiting in the unseen dimensions beyond the projection? Could the entire universe, every star, every planet, even the laws of physics themselves, be nothing more than a cosmic accident? Picture a vast, infinite ocean of higher dimensional space, where reality itself flickers in and out of existence like bubbles forming and popping in a boiling pot. Our universe might be just one of those bubbles, born from a random quantum fluctuation so tiny, so fleeting, that it defies comprehension. This is the mind-bending premise of cosmic inflation as a quantum event, where the Big Bang wasn't some singular, inevitable beginning, but a cosmic roll of the dice. Here's where it gets even stranger. If our universe is just one bubble in an endless multiverse, each with its own unique laws of physics, then the conditions we take for granted, gravity, light, even the stability of atoms, might be nothing more than a lucky draw. In some universes, matter might never have clumped into galaxies. In others, time could flow backward or loop in on itself. And in most, the constants of nature might be so hostile that life as we know it is impossible. This raises a haunting question. If the multiverse is real, is life a rare miracle or just an inevitable outcome in an infinite sea of possibilities? Scientists call this the Anthropic Principle, the idea that we observe the universe the way it is because, well, we're here to observe it. If the laws of physics were even slightly different, we wouldn't exist to ponder them at all. But what if it's deeper than that? Some theories suggest that quantum fluctuations in higher dimensions could create not just one universe, but an endless cascade of them, each with its own version of reality. Imagine standing in a hall of mirrors, except every reflection shows a completely different universe with its own rules, its own history, even its own version of you. The evidence for this radical idea might be hiding in the oldest light in the cosmos, the cosmic microwave background. Tiny temperature fluctuations in this afterglow could be the fingerprints of quantum ripples from the Big Bang, stretched across the sky by inflation. If these patterns match predictions, it would suggest that our universe really did burst into existence from a quantum seed. Even more intriguing are theories that collisions between neighboring bubble universes could leave detectable scars in the fabric of spacetime, like cosmic bruises etched into the night sky. But the most profound implication isn't just about how our universe began, it's about what it means for our place in the grand scheme of things. If the multiverse is real, then every possible outcome, every alternate history, every version of existence you can imagine might be playing out somewhere in the infinite expanse. It's a humbling thought that we might not be the center of the cosmos, but just one thread in an unimaginably vast tapestry of realities. And if that's true, it doesn't make us insignificant, it makes the fact that we're here at all even more extraordinary. Time might feel like an unstoppable river, carrying us from moment to moment in a neat, unbroken line, but what if that's just an illusion? Quantum gravity, the cutting-edge attempt to merge Einstein's relativity with quantum mechanics, paints a far stranger picture. In these models, time doesn't flow at all. Instead, past, present, and future might all exist simultaneously, frozen in place like frames in a cosmic film reel. Think of it like a novel. The story has a beginning, middle, and end, but the words on the page don't move, they're just there, waiting to be read. If this is true, then the ticking clock in your life isn't marking real progress. It's just a trick of perception, a way your brain makes sense of a universe where every moment is equally real. This idea shatters our most basic assumptions about cause and effect. If the future is already written alongside the past, does that mean your choices are just illusions? Some physicists argue that free will might be a kind of cosmic sleight of hand, a feeling generated by consciousness as it moves through a predetermined landscape. Picture a train on a track. You might feel like you're steering, but the rails were laid long ago. It's an unsettling thought, but here's the twist. Even if time is static, the experience of it is undeniably real to us. The question isn't just whether time flows, but why we perceive it so vividly if it doesn't. Where does this leave causality, the idea that one event leads to another? In a timeless universe, cause and effect might be labels we slap onto relationships that are deeper and more mysterious. Imagine a spiderweb where every strand touches every other, vibrating in perfect sync. In quantum gravity, events might not be linked in a straight line but woven together in a vast, interconnected network. A star exploding 1 billion years ago, and you reading this now, could be 2 points in a pattern far larger than time itself. So how do we test something so abstract? Clues might lie in black holes where gravity warps spacetime to its breaking point. If time is emergent, its fabric should fray at the smallest scales, revealing a graininess like pixels in a photograph that hints at the underlying timeless reality. Experiments with quantum particles already show that at microscopic levels, the order of events can become fuzzy, as if time itself is losing its grip. And if we ever detect gravitational waves from the earliest moments of the universe, their patterns might carry echoes of a timeless origin, a state where before and after had no meaning. The implications are dizzying. If time isn't fundamental, then aging, memory, even history itself might be secondary phenomena, side effects of a deeper physics we're only beginning to glimpse. It challenges us to ask, what does now really mean if every moment exists forever? And if the universe is a timeless tapestry, are we the threads or the hands that weave them? We've mapped the cosmos with stunning precision, planets orbiting stars, stars swirling around galaxies, galaxies clustered in vast cosmic webs. But there's a glaring puzzle. All of this visible matter isn't nearly enough to explain the gravity holding it all together. Enter dark matter, the invisible glue that makes up 85% of the universe's mass. But what if this mysterious substance isn't made of particles at all? What if it's something far stranger, a quantum field stretching across the cosmos, rippling through space like an invisible ocean? Think of the Higgs field, the quantum energy soup that gives particles their mass. Now imagine another field, even more elusive, weaving through the universe unnoticed. Unlike particles that bump and collide, this field could interact with ordinary matter only through gravity, tugging on stars and galaxies like an unseen hand. That's the radical idea behind dark matter as a quantum field, not discrete particles, but a pervasive, dynamic presence warping spacetime itself. Some theories suggest this field might vibrate in ways that create dense pockets, regions where gravity grows stronger, explaining why galaxies rotate faster than they should. Here's where it gets wild. If dark matter is a field, it could behave unlike anything in our particle zoo. Instead of clumping like dust, it might form vast, wave-like structures with peaks and troughs influencing galactic motion in rhythmic patterns. Picture dropping a stone into a pond. The ripples spread outward, invisible yet shaping everything they touch. Now scale that up to galactic proportions. These quantum ripples could be the hidden architects of the cosmos, sculpting the universe's large-scale structure while remaining utterly undetectable to our telescopes. But how do you look for something that doesn't emit, absorb, or reflect light? Scientists are turning to quantum interference, the same phenomenon that lets particles act as waves. If dark matter is a field, it might subtly alter the behavior of atoms in sensitive lab experiments, causing tiny shifts in their quantum states. Others study neutron stars, where extreme gravity could amplify interactions between ordinary matter and this hypothetical field, leaving faint imprints in the star's spin. Even more tantalizing, if this field exists, it might not be alone. Just as the Higgs has its particle, the Higgs boson, a dark matter field could have associated quanta, undiscovered particles that might briefly flicker into existence in high-energy collisions. The implications rewrite the rules. If dark matter is a quantum field, it means the universe isn't just filled with invisible stuff, it's saturated with an active, dynamic presence, a hidden layer of reality humming beneath the surface. It could mean galaxies are just the visible crests of deeper waves, floating on a sea of quantum energy we're only beginning to sense. And if we ever crack this mystery, it wouldn't just solve the missing mass problem, it would reveal a universe far more fluid, far more interconnected than we ever dreamed. After all, if gravity's shadow is a quantum field, what other invisible forces might be shaping reality right under our noses? Einstein's equations revealed a tantalizing possibility: hidden tunnels threading through the fabric of spacetime like cosmic subway lines. These are wormholes, theoretical bridges that could connect distant corners of the universe or even different moments in time. But here's the twist: while the math allows them, wormholes in their raw form would collapse instantly, crushed by their own gravity before anything could pass through. That's where quantum mechanics steps in, offering a bizarre solution. At the smallest scales, particles flicker in and out of existence, creating a seething sea of energy. Some physicists believe this quantum froth could act like microscopic scaffolding, propping open a wormhole just long enough for something or someone to slip through. Imagine a tunnel where one end hovers near a black hole where time slows to a crawl, while the other emerges near a young star billions of years in the past. Step inside and you might traverse not just space but epochs. Even wilder, quantum entanglement suggests wormholes could link parallel universes, where every choice you didn't make plays out in a reality just a tunnel away. Picture a vast cosmic network with wormholes as the subway lines connecting infinite versions of existence. It sounds like science fiction, but the equations don't lie. The universe might be threaded with these hidden passageways waiting to be discovered. The catch: traversable wormholes would require exotic matter with negative energy, a substance that defies gravity instead of succumbing to it. While we've never observed such matter, quantum theory hints it might exist in tiny amounts. In labs, the Casimir effect, where two metal plates in a vacuum experience a slight push from quantum fluctuations, suggests negative energy could be real. Scale that up and you might just stabilize a wormhole. But here's the paradox: if wormholes exist, they'd likely be microscopic, vanishingly small, or scattered in the quantum foam at the edge of spacetime. Finding one would be like searching for a single atom in a galaxy. Yet clues might lurk in the most violent places in the cosmos. When black holes collide, the gravitational waves they emit could carry subtle distortions, fingerprints of a hidden wormhole threading through the chaos. Others speculate that advanced civilizations, if they exist, might harness wormholes for travel, leaving behind detectable energy signatures. Whether natural or engineered, these spacetime shortcuts could rewrite the rules of exploration, turning a voyage across billions of light years into a stroll through a quantum doorway. The implications are staggering. Wormholes wouldn't just be cosmic curiosities, they'd challenge our deepest notions of distance, time, and separation. A universe knitted together by wormholes isn't vast and lonely, but intimate and interconnected, where every point touches every other. It's a vision of reality where the barriers between here and there, now and then, even this and that, are thinner than we ever imagined. And if that's true, the greatest adventures might not lie in crossing space, but in stepping through the cracks. What if the universe isn't the ultimate reality, but an intricate simulation running on some unfathomable computer? Imagine a civilization so advanced that they've mastered not just physics, but the very fabric of consciousness itself, capable of crafting entire worlds inside machines, indistinguishable from reality. Now ask yourself, if such beings exist, wouldn't the odds favor us being inside one of their creations rather than the original universe? This isn't just sci-fi speculation. Some of today's brightest minds take the simulation hypothesis seriously, and the clues might be hiding in the very laws of quantum mechanics. Take quantum indeterminacy, the idea that particles don't have definite states until they're observed. For decades, we've called this randomness, a fundamental feature of nature. But what if it's not randomness at all? What if it's the cosmic equivalent of rendering limitations, like a video game simplifying calculations to save processing power? Think of how a game only loads the graphics you're looking at right now, leaving the rest blurred or unrendered until needed. Quantum weirdness, from wave function collapse to entanglement, could be the universe's way of optimizing resources, only resolving details when an observer, a player, is present to witness them. Supporters of this idea point to the mathematical precision of the cosmos. The laws of physics aren't arbitrary, they're fine-tuned with constants so precise that even slight variations would make life impossible. Is this the work of a benevolent creator or the signature of a meticulous programmer? Even the speed of light, the universe's processing speed limit, starts to look suspiciously like a built-in safeguard against system overload. And then there's the holographic principle, which suggests all information in our 3D reality might be encoded on a 2D surface, exactly how we design a simulation to save memory. But how could we ever test this? Some researchers propose looking for glitches, tiny errors in the fabric of reality where the simulation cuts corners. These might show up as anomalies in high-energy particle collisions or sudden shifts in fundamental constants. Others suggest that if the universe is pixelated at the smallest scales, advanced experiments might detect this underlying resolution limit, like finding the pixels on a screen. Even quantum entanglement, with its instantaneous connections across space, could be a sign of optimized code, non-local variables linking distant parts of the simulation without processing every step in between. The implications are staggering. If we're in a simulation, it blurs the line between creator and creation. Are the beings running our universe also simulations themselves, nested in an infinite regression of virtual worlds? Does consciousness emerge from biology, or is it a user interface, a way for the simulation to experience itself? And if we ever prove this is all a construct, would that knowledge change the rules or crash the system? Yet here's the most humbling thought. Even if we're just lines of code in some cosmic program, our experiences, emotions, and discoveries are no less real to us. The universe might be a simulation, but the wonder it inspires, the questions it compels us to ask, those are as tangible as anything gets. And if that's true, then maybe the real mystery isn't whether we're in a simulation, but why someone or something wanted us to ask the question in the first place. Black holes aren't just cosmic vacuum cleaners. They might be the universe's most advanced quantum computers, humming with calculations at the edge of spacetime. Picture the singularity at a black hole's core, where matter is crushed to a point so small it defies physics as we know it. At that scale, the fabric of reality becomes a seething foam of quantum fluctuations, operating at resolutions so fine they're measured in Planck lengths, a billionth of a trillionth of a trillionth of a centimeter. It's here, in this unimaginably dense arena, that information might not be destroyed but transformed, rewritten into a language the universe itself can read. This idea builds on Stephen Hawking's groundbreaking realization: black holes aren't truly black, they emit radiation, slowly leaking energy into the void. But here's the twist: that radiation, now called Hawking radiation, might carry more than just heat. It could be etched with the very data of what fell into the black hole, like cosmic Morse code broadcasting the history of swallowed stars, planets, and light. If that's true, then every black hole could be a vault, preserving information in a form we're only beginning to decipher. Imagine a library where each book is written in the gravitational ripples of spacetime itself, waiting for a reader with the right quantum cipher. The mechanics behind this are stranger than fiction. Quantum theory suggests that information can never truly be lost. It can only scramble beyond recognition, like a shuffled deck of cards. Black holes might take this to the extreme, using their immense gravity to encode data in ways that blur the line between particle and wave, matter and energy. Some theories propose that the event horizon, the point of no return, acts like a holographic screen, storing information in 2 dimensions while the singularity processes it in 3. It's as if the black hole is running a cosmic algorithm, compressing the universe's secrets into a singularity-sized supercomputer. But how could we ever retrieve this data? Hawking radiation is faint, and decoding it would require technology far beyond our grasp. Yet the keys might lie in the radiation's quantum entanglement, the way particles emitted from the black hole remain mysteriously linked to its interior. If we could untangle these connections, we might glimpse fragments of what's inside, like reconstructing a shattered vase from the way its pieces fell. Future telescopes designed to detect subtle quantum signatures in the radiation could one day act as cosmic archaeologists, piecing together the stories of long-lost matter. The implications rewrite our understanding of reality itself. If black holes preserve information, then time and causality might be more flexible than we thought. A black hole's memory could span billions of years, holding snapshots of galaxies that no longer exist. It even raises the spine-tingling possibility that our universe, with all its history, could one day be reconstructed from the Hawking radiation of some distant epoch's black holes. We're not just looking at cosmic graveyards, we might be staring at the universe's backup drives, silently storing the data of existence itself. And if that's true, then every black hole is more than a monster of gravity. It's a storyteller whispering the universe's secrets in a language we're only beginning to hear. At the heart of quantum mechanics lies one of science's most bewildering riddles. The act of observation doesn't just measure reality, it seems to define it. In the famous double-slit experiment, particles behave as waves when unobserved, creating interference patterns on a screen. But the moment a detector is turned on, those waves collapse into definite particles, as if the universe is waiting for a conscious mind to make up its mind. This isn't just a quirk of tiny particles. What if this principle scales up, suggesting that sentience itself might be the cosmic architect, shaping galaxies and stars through the sheer act of perception? The idea that consciousness influences reality isn't new. Ancient philosophies spoke of the world as a dream or illusion shaped by the observer, but modern physics gives this notion startling weight. The measurement problem in quantum mechanics, the question of why observation forces probabilities into concrete outcomes, has no consensus explanation. Some interpretations, like the von Neumann-Wigner hypothesis, propose that consciousness itself is the trigger, the missing ingredient that transforms quantum potential into tangible reality. Imagine a universe where every star, every planet, exists in a fuzzy superposition until a mind, human or otherwise, focuses on it, like a cosmic version of the tree falling in an empty forest. But how could something as fragile as human awareness sway something as vast as the cosmos? One radical answer lies in entanglement. If particles remain mysteriously linked across space, could consciousness act as a universal entangler, weaving disparate quantum events into a coherent whole? Think of the universe as a canvas of pure potential, with each conscious observer adding brushstrokes, collapsing probabilities into the shared reality we experience. Even more bizarre, if consciousness plays this role, might advanced civilizations or future forms of intelligence influence the universe's evolution on grand scales, steering cosmic expansion or the birth of stars through collective observation? Critics argue this veers into metaphysics, but intriguingly, there are testable angles. If consciousness collapses wave functions, then large-scale systems isolated from observers, like distant galaxies, might behave differently than those under scrutiny. Some researchers propose scanning the cosmic microwave background for anomalies, regions where quantum fluctuations remain unresolved due to lack of observation. Others suggest laboratory experiments with increasingly complex conscious observers, from humans to AI, to see if the collapse mechanism changes. The results could redefine not just physics but our place in the universe. The implications ripple far beyond science. If consciousness molds reality, then the universe isn't a cold, indifferent machine. It's a participatory drama, a collaboration between mind and matter. It raises spine-tingling questions. Are we accidental witnesses, or is the cosmos somehow designed to be observed? Could our collective attention be quietly steering the universe toward complexity, even beauty? And if so, what happens when we're no longer here to look? The answer might lie in the quantum fog, waiting for the next conscious glance to bring it into focus. Every decision you make, from what you eat for breakfast to the career you choose, might not just alter your future, it could spawn an entirely new universe. This isn't science fiction, it's the radical promise of the many worlds interpretation of quantum mechanics. Imagine flipping a coin. In our world, it lands heads. But according to this theory, the moment that coin hovered in the air, reality itself split, one universe where it landed heads, another where it landed tails, and countless others where it never landed at all, caught in a gust of wind or snatched by a passing bird. Now scale that up. Every quantum event, every particle's random wiggle doesn't just happen one way, it happens every possible way, each outcome playing out in its own branching timeline. What's truly staggering is how this applies to the cosmos itself. The universe's expansion, the formation of galaxies, even the laws of physics might not be fixed. They could be just one version of countless possibilities. Picture a multiverse where inflation never ended, and space keeps stretching infinitely fast, leaving stars and planets too far apart to ever meet. Or a timeline where dark energy is weaker, causing the universe to collapse back into a big crunch before life could emerge. In some branches, gravity might be stronger, squeezing stars into black holes before they could ignite. In others, electromagnetism could be so feeble that atoms never form. We don't just live in a universe fine-tuned for life. We live in the slice of the multiverse where, against ludicrous odds, the dice rolled in our favor. The math behind this is both elegant and mind-numbing. Quantum wave functions, which describe probabilities, don't collapse into single outcomes. They keep evolving, with every possibility remaining real but separated into non-interacting branches. Think of it like a cosmic choose-your-own-adventure book where every page is turned simultaneously, each leading to a different ending. Hugh Everett, the physicist who proposed this in the 1950s, argued that these branches aren't just mathematical abstractions. They're as real as the universe we see, even if we can't access them. But if these parallel worlds exist, where are they? The answer might lie in higher dimensions, realms beyond our four-dimensional spacetime. Imagine a sheet of paper, flat, two-dimensional. Now stack infinite sheets together, each a separate universe, slightly shifted along a dimension we can't perceive. To us, these worlds are invisible, like shadows passing behind a curtain. Yet some theories suggest that gravity, the weakest but most far-reaching force, might occasionally leak between these branes, creating subtle tremors in our universe. Future gravitational wave detectors could one day catch these echoes, the faint whispers of our cosmic neighbors. The implications are dizzying. If the many worlds interpretation is correct, then somewhere out there, a version of you chose differently at every crossroads. A version where you never watched this video, a version where humanity never left Earth, a version where the dinosaurs still rule. It's a humbling thought that our choices matter not just here, but in the infinite tapestry of realities they weave. And if that's true, then the universe isn't just vast, it's limitless, a fractal of possibilities where every what if is a somewhere. The real question isn't whether these worlds exist, but what it means for us to be alive in this one, right now, threading our unique path through the quantum maze. Picture absolute nothingness, not empty space, but the true void where not even time or dimensions exist. Now imagine a flicker, a fleeting quantum hiccup in that void, so small it makes an atom look like a galaxy. In that fragile moment, a universe could have been born. This is the startling possibility of quantum tunneling birthing the cosmos, the idea that our entire existence might be the result of a random fluctuation so rare, so improbable that it defies comprehension. But here's the twist: if it happened once, why couldn't it happen an infinite number of times? Quantum tunneling is one of the strangest phenomena in physics. Normally, particles need energy to overcome barriers like a ball rolling uphill. But at the quantum scale, particles can suddenly appear on the other side of barriers without crossing, as if teleporting. It's like throwing a tennis ball at a wall and watching it vanish from your hand only to reappear on the other side. Now apply that to the birth of the universe. If true nothingness has a kind of quantum energy, what physicists call vacuum energy, then it's possible for a bubble of spacetime to tunnel into existence, inflated by its own instability. The Big Bang might not have been an explosion at all, but a quantum leap from nothingness into somethingness. This leads to a breathtaking implication. If universes can pop into existence this way, then ours might be just one bubble in an endless cosmic foam. Eternal inflation theory suggests that once space starts expanding, it never truly stops in some regions, creating infinite pocket universes with different physical laws. Some might collapse instantly, while others, like ours, stabilize long enough for stars and life to form. And just as our universe emerged from quantum chaos, it might one day spawn new universes of its own, through black holes, quantum fluctuations, or processes we can't yet fathom. The evidence for this radical idea might be hidden in the cosmic microwave background, the leftover glow from the Big Bang. If our universe tunneled into existence, subtle patterns in this ancient light could carry the fingerprints of that primordial quantum jump. Even more intriguing are theories that black holes, those cosmic vacuum cleaners, might actually be birthing new universes in their cores, their singularities acting as cosmic umbilical cords. It's a dizzying thought. Every black hole in our sky could be a doorway to another reality, with its own laws, its own history, even its own version of the quantum tunneling story. But the deepest question remains: if universes can emerge from nothing, does nothingness itself have rules? Is there a meta-law that governs the bubbling of spacetime into existence? Or is the multiverse an endless, chaotic experiment where every possible configuration of reality plays out somewhere in the quantum foam? Either way, one thing is certain: the universe isn't just stranger than we imagine. It might be stranger than we can imagine, a cosmic jack-in-the-box that's still springing surprises. And if that's true, then the greatest mystery isn't how our universe began, but how many times it's happened before, and how many times it will happen again. Time feels like an arrow flying in one unshakable direction, from past to future, from order to chaos. You can scramble an egg, but no matter how hard you try, you'll never see it uncook itself. This stubborn asymmetry is called entropy, the universe's tendency toward disorder, and it's the only law of physics that seems to care about the past and future differently. But here's the enigma: at the quantum level, most laws are perfectly reversible. Particles don't care if time runs forward or backward, so why does the universe? The answer might lie in one of quantum mechanics' most baffling phenomena, entanglement, and it could rewrite our understanding of time itself. Imagine two entangled particles dancing in perfect sync no matter how far apart they drift. Change one and the other responds instantly, as if space and time don't exist between them. Now picture this happening trillions upon trillions of times, every moment across the cosmos. Some physicists argue this endless web of quantum connections isn't just a curiosity, it's the engine driving entropy forward. Every time particles entangle, they create new correlations, new layers of complexity that can't be undone without unraveling the entire system. It's like shuffling a deck of cards. You can easily mix them up, but restoring the original order becomes statistically impossible. Entanglement might be the universe's ultimate shuffler, ensuring time marches in one direction by weaving an ever more tangled quantum tapestry. This leads to a breathtaking idea. If entanglement fuels entropy, then the arrow of time isn't just a feature of our universe, it's a consequence of quantum relationships stretching back to the Big Bang. In the early cosmos, particles were simpler, less entangled. But as the universe expanded, interactions multiplied and entropy soared. The cosmic microwave background, the faint glow from the universe's infancy, might hold clues. Its subtle imperfections could be the fossilized imprints of those first quantum links, the seeds of time's irreversible flow. But here's where it gets mind-bending. If time's direction depends on entanglement, could we hypothetically reverse it? Some theories suggest that in a universe collapsing under gravity, a so-called Big Crunch entanglement might unwind, decreasing entropy and making time run backward. Particles would disentangle, correlations would simplify, and cause and effect would flip. A dying star might reassemble from scattered gas. A shattered glass would leap back onto the table. Of course, we have no way of testing this, but the math doesn't forbid it. The implications stretch beyond physics. If entanglement shapes time, then our perception of past and future isn't just psychological, it's woven into the quantum fabric of reality. Every memory, every aging cell, every fading star might trace back to those invisible quantum threads, silently steering the universe from order to chaos. And if that's true, then time isn't just something we measure with clocks. It's the universe keeping score, counting the uncountable quantum handshakes that bind everything together, one irreversible moment at a time. The Higgs field is often described as cosmic molasses, a sticky energy soup that slows particles down and gives them mass. Without it, atoms would zip around at light speed, never clumping into stars or planets or you. But what if this same field, responsible for the very structure of matter, has a hidden dark side? Some theorists suggest the Higgs might not just shape the universe, it could be quietly ripping it apart. Here's the paradox: the Higgs field is thought to be stable, its value finely tuned to allow chemistry, biology, and life. But quantum theory hints that stability might be an illusion, a temporary calm before a catastrophic phase transition. Picture a valley surrounded by mountains with the Higgs sitting comfortably at the bottom. But what if there's a deeper valley, a lower energy state the field could tumble into? If that happened, the laws of physics as we know them would rewrite themselves overnight. Atoms would dissolve, forces would unravel, and space itself might recoil with violent expansion. A second Big Bang triggered not by a singularity, but by a quantum hiccup in the Higgs. Even wilder, this process might already be happening. The Higgs field could be fluctuating in ways that subtly contribute to dark energy, the mysterious force accelerating cosmic expansion. Think of it like a pot of water simmering on low heat. Tiny bubbles form and pop, each releasing a whisper of energy. Across the universe, countless Higgs fluctuations might add up, pushing galaxies apart faster and faster. It's a haunting thought. The same field that makes solid reality possible could also be the engine of its dissolution. The evidence is speculative but tantalizing. If the Higgs is metastable, not truly stable but trapped in a false low, then experiments at particle colliders might detect its fragile state. The mass of the Higgs boson around 125 times heavier than a proton suggests the field is just stable enough for our universe to exist. For now, but in a trillion years, a quadrillion, the math allows for a tipping point where quantum randomness kicks the field over the edge, rewriting physics in a cosmic blink. What would that look like? Picture a bubble of true vacuum where the Higgs has settled into its lowest state, expanding at light speed. Inside this bubble, fundamental forces reconfigure, atoms disintegrate, and space-time itself might recoil. The shockwave would be unstoppable, not because it's violent, but because it changes the rules. Even light couldn't outrun it, since the speed of light itself would be redefined. The universe wouldn't end with a bang or a whimper, but with a rewrite, a silent conversion to a new set of physical laws where life as we know it is impossible. Yet there's a strange comfort in this fragility. If the Higgs is a time bomb, it's one with a fuse so long we'll never hear it tick. More importantly, its precarious balance might explain why the cosmos is expanding at all. The Higgs isn't just the sculptor of mass, it could be the unseen hand behind the greatest mystery in modern cosmology. And if that's true, then every atom in your body isn't just a product of the Higgs field. It's a temporary ripple in a quantum ocean that might, one distant day, swallow itself whole. At scales a billion trillion times smaller than an atom, space-time isn't the smooth, stretchy fabric we imagine. It's a seething, chaotic froth, bubbling with virtual particles that flicker in and out of existence like cosmic static. This is quantum foam, the turbulent foundation of reality itself, where the very concepts of here and now break down into a probabilistic dance. Picture the surface of a stormy ocean, but instead of waves, it's spacetime itself that's churning, with microscopic black holes and wormholes forming and vanishing in trillionths of a second. It's a realm so bizarre that even time loses its meaning, looping back on itself or branching into fractal possibilities. Now zoom out to the cosmic scale. Could this frothiness, this fundamental graininess of spacetime, be the hidden architect of dark energy? Some theories suggest that quantum foam isn't just microscopic noise, it might generate a sort of pressure, an energy inherent to the vacuum of space itself. Think of it like the hum of a refrigerator, unnoticeable up close, but if you had trillions of them humming in unison, the collective buzz could push galaxies apart. If true, dark energy wouldn't be some exotic force but the cumulative effect of spacetime's ceaseless quantum jitter, a cosmic background vibration stretching the universe from the bottom up. But quantum foam might leave other fingerprints too. Gravitational waves, the ripples in spacetime from colliding black holes, could carry subtle distortions if they've traveled through this frothy medium. Imagine sound waves passing through water. If the water is turbulent, the sound gets scrambled. Similarly, if spacetime is foamy, gravitational waves might arrive slightly scuffed, bearing the marks of their journey through the quantum chaos. Future detectors, 1,000 times more sensitive than today's, could hunt for these anomalies, offering the first direct evidence that spacetime isn't smooth but pixelated, like a digital image zoomed in too far. The implications rewrite our understanding of the cosmos. If spacetime is foam at its core, then black holes might not be singularities but knots in the quantum turbulence, regions where the foam tangles into self-sustaining vortices. Even the speed of light, the universe's ultimate speed limit, could vary slightly in this froth, a heresy in Einstein's relativity, but a tantalizing possibility for quantum gravity. Some models suggest that high-energy cosmic rays, particles racing from distant galaxies, might arrive with tiny timing differences, as if they've navigated an invisible obstacle course of quantum bubbles. Yet the wildest idea is this: if quantum foam is real, it could mean the universe has a resolution limit, a smallest possible scale where reality itself becomes blurry. Beyond that point, the questions where and when might not even have answers. It's a humbling thought that the cosmos isn't just stranger than we imagined, but stranger than we can imagine, built on a foundation of chaos that defies every intuition. And if we ever prove it, we won't just uncover the texture of spacetime. We'll glimpse the raw code of existence, written in a language of foam and flicker, where every vacuum teems with infinite potential. Einstein spent his later years haunted by quantum mechanics, convinced that its randomness was an illusion, a veil hiding deeper, deterministic laws. He famously declared that God does not play dice with the universe, suggesting that particles only appear to behave unpredictably because we haven't uncovered the hidden gears turning behind the curtain. These hypothetical mechanisms, known as hidden variables, could rewrite not just quantum theory, but our understanding of cosmic expansion itself. What if dark energy isn't some mysterious force, but the shadow of unseen subatomic rules playing out on a universal scale? Picture a cosmic puppet show where stars and galaxies dance to the tune of invisible strings, variables so subtle they've eluded detection. In this view, the universe's accelerating expansion isn't random or driven by dark energy, but orchestrated by these deeper laws. It's like watching ripples on a pond without realizing a current flows beneath. Some theories propose these variables could act as cosmic constraints, weaving quantum uncertainty and cosmic destiny into a single framework. Instead of particles popping into existence at random, their behavior, and by extension, the behavior of everything they compose, might follow a hidden script written at the birth of the universe. The implications ripple across physics. If hidden variables exist, they could resolve the tension between quantum weirdness and Einstein's beloved determinism. Take entanglement. Two particles instantly influencing each other across light years seems magical, unless they're both responding to a shared, unseen variable set in motion long ago. This could mean the universe operates like an intricately wound clock, its expansion and quantum quirks all part of a grand, predetermined design. Even the apparent randomness in radioactive decay or photon emission might just be our ignorance of the underlying rules. Critics argue that experiments have ruled out local hidden variables, those confined by spacetime. But what if these variables are non-local, operating beyond the dimensions we perceive? Imagine a higher dimensional chessboard where moves in one plane dictate outcomes in another. The universe's expansion could be one such outcome, guided by variables we can't yet measure. Some physicists speculate these hidden rules might manifest in the large-scale structure of the cosmos, subtly sculpting galaxy clusters or fine-tuning the cosmic microwave background's faint imperfections. The hunt for these variables is already underway. Quantum experiments testing Bell's theorem, a mathematical proof distinguishing randomness from hidden determinism, keep pushing boundaries. Others study anomalies in cosmic expansion, asking whether dark energy's uniformity hints at a deeper order. If hidden variables are real, their discovery wouldn't just demystify quantum mechanics. It could reveal the universe as a vast, interconnected equation where every particle's spin and every galaxy's flight follow an elegant, if invisible, logic. Einstein might have been onto something after all. The universe's greatest mysteries, from quantum leaps to cosmic acceleration, could be threads of a single, hidden tapestry. And if we ever pull that thread, we might find that randomness was never the rule, just the signature of a reality far more intricate than we dared to dream. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through a light year of lead without a single interaction. Trillions stream through your body every second, leaving no trace, as if reality itself is barely a suggestion to them. But what if these spectral particles, long dismissed as cosmic background noise, are hiding the key to one of physics' greatest mysteries? Some theorists propose that neutrinos, with their bizarre quantum properties, might be whispering the secrets of dark energy directly to the fabric of spacetime. Here's the twist: while neutrinos barely interact with matter, they do interact with gravity. And in the vast emptiness of space, where matter is sparse but gravity reigns supreme, these particles could be exerting a subtle push on the cosmos. Imagine blowing on a dandelion. Your breath doesn't touch every seed, but the ripple effect spreads them outward. Similarly, neutrinos, born in the nuclear furnaces of stars and cataclysmic supernova, might collectively nudge the universe's expansion, their combined influence amplifying over billions of years. The math gets stranger. Neutrinos oscillate, changing flavors between electron, muon, and tau as they travel, a quantum quirk that hints at an intrinsic connection to spacetime itself. If these oscillations are tied to dark energy's repulsive force, then every time a neutrino shifts identity, it could be tweaking the vacuum energy of empty space, like a cosmic dial adjusting the universe's expansion rate. Even more tantalizing, some models suggest that neutrinos might interact with an undiscovered field permeating the cosmos, a hidden partner to dark energy that only reveals itself through these ghostly particles. But how do you catch a shadow? Scientists are racing to detect ultra-high-energy neutrinos from the distant universe, hunting for anomalies in their behavior that could betray a link to dark energy. Others study the cosmic neutrino background, the faint afterglow of the Big Bang's first second, for patterns that align with accelerating expansion. Even more radical, if neutrinos are dark energy messengers, their quantum fuzziness might leave imprints on large-scale structures, galaxy clusters aligned in ways that only make sense if these particles are quietly shaping spacetime from within. The implications are staggering. If neutrinos influence cosmic acceleration, it would mean the universe's fate is tied to the most insubstantial particles we know. Not through their mass or energy, but through their quantum ballet, a dance so subtle we've barely begun to hear the music. It's a humbling thought that the answer to dark energy might not lie in some exotic substance or force, but in particles we've known about for decades, whispering truths we're only now learning to hear. And if that's true, then the universe's greatest mystery might be hiding in plain sight, flowing through your hands, your walls, even your bones, unnoticed but undeniable. Gravity shapes the cosmos, bending planets into orbits and galaxies into spirals. But what if this force we take for granted isn't a fundamental part of nature at all? What if it's more like temperature, a large-scale effect that emerges from countless tiny, invisible interactions? That's the jaw-dropping premise of gravity as an emergent quantum force, where the weight of a star or the curve of spacetime itself might be nothing more than the collective behavior of entangled quantum bits flickering in the void. Picture an ocean on a windless day, calm, smooth, almost solid, but zoom in, and you'll see it's made of trillions of water molecules, each jostling chaotically. The ocean's surface tension isn't a separate force, it's the net result of all those molecular dances. Now imagine spacetime the same way. Gravity, in this view, isn't a standalone phenomenon but a side effect of quantum entanglement, a kind of cosmic peer pressure where particles, linked across vast distances, conspire to create the illusion of a gravitational field. Step on a scale, and the number you see might not reflect a force pulling you down, but the sum of a universe's worth of quantum handshakes beneath your feet. This idea turns Einstein's relativity on its head. Instead of mass-warping spacetime, or rather, the illusion of it could arise from something deeper. In some models, every particle carries a tiny bit of quantum information, like a cosmic ID tag. When these bits entangle, their relationships create a network, a hidden scaffolding that, when viewed from afar, looks like the smooth, curving fabric of general relativity. It's as if gravity is the universe's way of averaging out quantum chaos, the way a TV screen blends pixels into a seamless image. The implications are staggering. If gravity emerges from entanglement, then black holes, those gravitational monsters, might just be regions where quantum connections are so dense they knot spacetime into a singularity. Even the Big Bang could be reinterpreted, not an explosion in space, but the moment when the first quantum bit snapped into sync, birthing both matter and the stage it moves on. And dark energy, that might be the faint tension of entanglement stretching thin as the universe expands, like a cosmic rubber band losing its grip. But how do we test something so abstract? Clues might lie in the quantum behavior of spacetime itself. If gravity is emergent, then at the smallest scales, space should shimmer with statistical noise like static on a radio, hinting at the underlying quantum chatter. Experiments with ultra-sensitive gravity probes or studies of entanglement in exotic materials could one day catch this noise in action. Others look to black holes, theorizing their event horizons might act as entanglement amplifiers, where the pull of gravity directly mirrors the strength of quantum links. The most mind-bending possibility, if this theory holds, it means the universe isn't just described by quantum mechanics, it is quantum mechanics all the way up. There's no separate gravitational layer, just an ocean of entangled bits and the waves we call gravity. It's a vision where the cosmos isn't built on space and time, but on connections, an infinite web of quantum relationships, whispering the illusion of weight, motion, and the very ground beneath your feet. And if that's true, then falling isn't a force tugging you down, it's the universe remembering how to hold you. In a cosmos stretched across eternity, where time and space sprawl without end, the laws of probability twist into something unsettling. Given enough time, trillions upon trillions of years, even the most improbable events become inevitable. And that includes the spontaneous formation of a fully formed, self-aware brain, complete with memories and senses floating alone in the void. This is the Boltzmann brain paradox, a thought experiment so bizarre it forces us to question whether we're real or just fleeting figments of quantum chaos. Picture a universe where entropy reigns supreme, where particles jostle endlessly in the dark. Every so often, purely by chance, they arrange themselves into something improbable, a snowflake, a diamond, even a living creature. Now stretch that possibility to its extreme, a functioning brain, complete with fabricated memories of an entire life, hallucinating a world that doesn't exist. The odds are vanishingly small, but in an infinite universe with infinite time, they're not zero. In fact, statistically, Boltzmann brains named after the physicist Ludwig Boltzmann should outnumber real, biologically evolved minds by an unimaginable margin. So why does the world feel so solid? Why does history hold together? Are you reading this script, or is your momentary consciousness just a blip in the void, destined to dissolve as quickly as it formed? The paradox cuts to the heart of cosmology. If our universe truly is infinite and eternal, then Boltzmann brains aren't just possible, they're inevitable. Worse still, they're more likely than us. After all, conjuring a single, self-aware brain from random fluctuations requires vastly less energy than crafting an entire universe with galaxies, planets, and billions of years of consistent history. From a probability standpoint, it's far simpler for you to be a momentary accident than a product of cosmic evolution. This isn't just philosophy, it's a crisis for modern physics. If the math says we're probably hallucinations, how can we trust any observation, any experiment, any truth? Yet the universe feels real. The coffee in your mug stays warm, the stars obey predictable motions, and the laws of physics hold firm across billions of light years. Some scientists argue this consistency is the best evidence against the Boltzmann brain hypothesis. If we were random fluctuations, reality would glitch, memories would shift, gravity might wobble, time could stutter. Others propose a grim resolution. Maybe the universe isn't infinite after all. If space or time has limits, if there's a true end to cosmic history, then the window for Boltzmann brains to form slams shut before they outnumber real minds. But here's the twist that keeps physicists awake at night. The paradox might be pointing to something deeper about existence itself. Consciousness, perception, even the arrow of time could be part of a larger structure we don't yet understand. If Boltzmann brains are impossible, what does that say about the nature of reality? And if they're possible, well, how would you ever know you weren't one? The only comfort is this: for now, in this moment, the world holds together, and maybe that's enough. After all, hallucinated or not, the questions still matter, and the answers, if they exist, are out there waiting. Consider the humble bacterium blindly mutating, adapting, surviving against impossible odds through sheer persistence. Now imagine the universe itself undergoing a similar process, not through biological struggle, but through quantum trial and error. This is the spine-tingling premise of quantum Darwinism, where the stability of our physical laws isn't just a happy accident, but the result of a cosmic survival of the fittest. At the quantum level, particles exist in superpositions, ghostly states of maybe, where electrons spin both clockwise and counterclockwise until observation forces a choice. But why does the macroscopic world feel so solid? Why don't chairs or planets exist in fuzzy probabilities? The answer might lie in decoherence, the process where quantum systems interact with their environment, collapsing into definite states. Think of it like a game of telephone. The more a quantum state gets measured by bouncing off atoms, photons, or dust particles, the more its fragile superposition erodes, leaving behind the classical reality we recognize. Now stretch this idea across the multiverse. If countless universes bubble into existence with random physical constants, some where gravity is too weak for stars, others where electromagnetism crushes atoms. Only those with the right balance of stability and complexity persist long enough to host observers. It's not that the universe was designed for life. Life emerged in the universe that didn't self-destruct. Quantum decoherence acts as the filter, weeding out unstable configurations until what remains are worlds where particles reliably form galaxies, planets, and minds capable of asking why. The fingerprints of this selection might be hidden in the very fabric of reality. Take the cosmological constant, the value governing dark energy's repulsive force. It's fine-tuned to an absurd degree. Alter it by 1 part in a trillion, and the universe either rips itself apart or collapses instantly. Critics call this luck. Quantum Darwinism suggests its inevitability. Only in universes where the constant falls within this razor-thin margin can structures like galaxies and physicists arise to measure it. But here's where it gets radical. If quantum Darwinism shapes universes, could it also shape conscious observation itself? Some interpretations propose that consciousness isn't just a passive bystander, but an active participant in cosmic selection. In this view, the act of observation doesn't merely record reality, it helps stabilize it, like a tree's roots preventing soil erosion. The more observers a universe produces, the more real it becomes, creating a feedback loop where life and physics co-evolve. The implications rewrite our place in the cosmos. We're not just accidents of chemistry in an indifferent universe. We're part of a self-reinforcing cycle where existence gazes back at itself, each observation reinforcing the laws that made it possible. And if that's true, then the deepest question isn't why we're here. It's whether we, by being here, are quietly shaping the universe just as it shaped us. Hidden in the depths of the universe, beyond countless galaxies, lies a gravitational enigma so powerful it tugs entire clusters of stars toward it at staggering speeds. Astronomers call it the Great Attractor, a cosmic mystery that defies explanation. Picture a swirling drain in the ocean, pulling everything toward it. Except this isn't water, but galaxies spanning hundreds of millions of light years, all streaming toward an invisible force. The strangest part, we can't see what's doing the pulling. This isn't just a supermassive black hole or a cluster of dark matter. The scale is too vast, the physics too bizarre. So what if the answer lies not in the realm of stars and planets, but in the quantum underworld of spacetime itself? One radical theory suggests the Great Attractor might be a relic from the universe's birth, a cosmic scar left behind when the fabric of spacetime cooled and solidified after the Big Bang. Think of it like ice forming on a pond. As water freezes, tiny cracks and imperfections emerge. On a cosmic scale, these imperfections could manifest as vacuum defects, regions where spacetime never quite smoothed out, creating knots of distorted gravity. If such a defect exists in our cosmic neighborhood, it could explain the Great Attractor's pull without requiring unimaginable amounts of hidden matter. It wouldn't be an object at all, but a flaw in the very structure of reality, a gravitational pothole on the highway of the cosmos. But there's an even wilder possibility. The Great Attractor might not be a defect but a rift, a tear in spacetime where the laws of physics fray at the edges. Some models of quantum gravity allow for cosmic strings, ultra-thin filaments of energy left over from the early universe, thinner than an atom but denser than a neutron star. If one of these strings pierced our region of space, its immense gravity could drag galaxies toward it like iron filings to a magnet, even more unsettling. These strings could theoretically vibrate, sending shockwaves through spacetime that ripple across billions of light years, subtly steering the motion of everything in their path. The challenge is catching this phantom in action. The Great Attractor lies obscured by the Milky Way's own galactic dust, hidden behind a curtain of stars we call the zone of avoidance. But new telescopes peering through radio and X-ray wavelengths are beginning to pierce that veil, mapping the strange flows of galaxies with unprecedented precision. If the anomaly stems from quantum-scale phenomena, its fingerprints might appear in the cosmic microwave background, the afterglow of the Big Bang, as subtle temperature variations or twisted patterns in the polarization of ancient light. Others hunt for evidence in the peculiar motions of galaxy clusters, tracing their trajectories like breadcrumbs leading to the heart of the mystery. What's at stake isn't just solving a cosmic whodunit. If the great attractor's roots are quantum, it would mean the universe's largest structures are sculpted by its smallest rules, a bridge between the infinitesimal and the infinite. It would suggest that spacetime isn't just a stage for matter, but an active participant capable of twists and tangles that shape the fate of galaxies. And if that's true, then the cosmos isn't just expanding, it's being pulled, gently but inexorably, by shadows from its own quantum past. Time crystals sound like something ripped from a science fiction novel, structures that don't just exist in space, but in time, oscillating in perfect, perpetual motion without any energy input. Unlike ordinary crystals where atoms arrange themselves in repeating patterns across space, time crystals repeat their states over time, ticking like quantum metronomes locked into an eternal rhythm. Now imagine these bizarre objects not in a lab, but in the seething chaos of the early universe, moments after the Big Bang. If they existed, their bizarre properties could have sculpted the very fabric of reality, leaving echoes in the galaxies and cosmic webs we see today. Think of the infant universe as a quantum soup, hotter and denser than anything we can recreate. In that primordial frenzy, fleeting time crystals might have formed spontaneously, their atomic lattices cycling through configurations not just in space, but across microseconds of cosmic time. These wouldn't be crystals as we know them, they'd be more like ripples in the fabric of causality itself, imprinting their rhythmic pulses onto the swirling plasma. As the universe expanded and cooled, those ripples could have frozen into the seeds of structure, guiding matter to clump into galaxies and clusters along ghostly grooves left behind by their oscillations. The evidence for this wild idea might be hiding in the cosmic microwave background, the afterglow of the Big Bang. If time crystals once pulsed through the early universe, their vibrations could have left faint patterns in this ancient light, like whispers trapped in amber. Some models suggest these patterns would appear as subtle asymmetries in the temperature fluctuations, deviations from the uniform randomness we'd expect. Even more tantalizing, if time crystals were entangled, linked across vast distances through quantum weirdness, their synchronized beats could explain why the universe looks so eerily uniform on large scales, as if distant regions were somehow choreographed despite never being in contact. But here's the twist: time crystals, by definition, exist in their lowest possible energy state. They don't do anything in the traditional sense, they just are, ticking endlessly without fuel or friction. So how could something so passive shape something as dynamic as the cosmos? The answer lies in their resilience. While other quantum fluctuations flickered and vanished, time crystals would have endured, their stable rhythms acting like cosmic tuning forks, gently nudging matter into place over eons. In a sense, they'd be the universe's first clocks, not just marking time but imprinting it onto the structure of everything. The implications stretch beyond cosmology. If time crystals seeded cosmic structure, it means the universe's largest features, galaxy clusters spanning millions of light years, might trace back to quantum phenomena that defy our classical intuition. It suggests a reality where time isn't just a backdrop but an active participant in creation, where the tiniest ticks of quantum clocks reverberate across billions of years. And if that's true, then the cosmos isn't just expanding, it's dancing, moving to a rhythm set in motion at the dawn of time itself. At the quantum level, particles flirt with multiple realities, existing in a haze of possibilities until an observation pins them down to a single state. But what if this isn't just a microscopic quirk? What if the entire cosmos, from the swirl of galaxies to the dust on your bookshelf, once lingered in a similar superposition, not yet real, not yet fixed, but a swirling potential waiting to be measured? This is the staggering implication of quantum superposition scaled to the universal. The idea that before any observer, the universe itself might have been a kaleidoscope of overlapping realities, each as valid as the next. Consider the double-slit experiment, where a single photon behaves as both particle and wave until observed. Now stretch that logic to the Big Bang. In its earliest moments, the universe was smaller than an atom, a realm where quantum rules reigned supreme. If superposition applies, then the newborn cosmos didn't just take one path, it took every path simultaneously. One version birthed stars, another collapsed instantly. One spawned life, another remained a void. All these destinies existed at once, a cosmic Schrödinger's cat in a box the size of existence itself. Only when something or someone peeked inside did the universe choose its timeline, collapsing into the reality we now call home. This raises a haunting question: who or what was the first observer? If the universe needed measurement to solidify, then consciousness isn't just a byproduct of physics, it's a prerequisite for reality. Some interpretations suggest that quantum fluctuations in the early universe might have acted as rudimentary observers, each tiny interaction chiseling away at the fog of possibilities. Others propose that the universe's sheer complexity forced a collapse, like a house of cards too unstable to remain standing, but the most radical idea. That observation is woven into the fabric of spacetime, a feature as fundamental as gravity or light, with no single first moment but a gradual crystallization of reality from potential. The evidence for this theory is speculative but tantalizing. If the universe emerged from a superposition, its quantum origins might have left fingerprints in the cosmic microwave background, subtle anomalies where probabilities briefly flickered before solidifying. Some models even suggest that alternate versions of the universe, branches that collapsed into other realities, could have brushed against ours, leaving gravitational echoes in the large-scale structure of galaxies. Future telescopes sensitive enough to map these ultra-faint ripples might one day catch whispers of the paths not taken, like shadows of worlds that almost were. But the deepest implication isn't about the past, it's about the present. If superposition holds at cosmic scales, then reality might be more malleable than we think. Every observation, every measurement could be quietly reinforcing the universe's structure, like a spider weaving a web that also sustains itself. It's a humbling thought that the cosmos isn't just something we observe, but something we participate in, a dance of possibilities where the steps are still being written and we're all part of the choreography. The universe is dying slowly, inevitably. Stars will burn out, galaxies will drift apart, and in trillions upon trillions of years, the cosmos as we know it will fade into a cold, silent darkness. But what if death isn't the end? What if the universe's final gasp isn't a whimper but a cosmic reset button? This is the Omega Point theory, a breathtaking vision where the end of everything becomes the seed of something new, and where consciousness, against all odds, might just hitch a ride into the next cycle. Picture the universe's final moments, black holes, the last bastions of order, slowly evaporating through Hawking radiation, their energy leaking into the void. As space stretches thinner and colder, quantum fluctuations, those tiny, unpredictable pops of energy that birthed the cosmos, could once again take center stage. In this unimaginably distant era, the vacuum of space might grow so unstable that a single quantum tremor could trigger a new Big Bang, a fresh universe budding from the ashes of the old. It's like a phoenix rising, but on a scale so vast it defies comprehension. A cosmic rebirth built into the fabric of reality itself. Here's where it gets stranger. Some theorists, like physicist Frank Tipler, argue that this final state, the omega point, might not just be a new universe, but a kind of transcendent singularity where information, structure, and even consciousness could somehow survive the transition. Imagine a future civilization, billions of years advanced, harnessing the dying embers of the cosmos to encode their knowledge, their very essence, into the quantum fluctuations that will birth the next universe. In this view, the laws of physics in our universe might not be accidental, but carefully tuned by predecessors in a cycle older than time. But how could consciousness possibly leap across the abyss between universes? One radical idea leans on quantum entanglement. If entangled particles can link across space, might entangled information link across time or even across cosmic cycles? Think of it like a message in a bottle tossed into the surf of one universe and washing ashore in another. If quantum states can imprint on the fabric of spacetime itself, then the final moments of one cosmos could etch themselves into the first moments of the next, carrying echoes of what came before. The implications blur the line between physics and philosophy. If the omega point is real, it suggests an almost poetic symmetry to existence, a universe that dies only to be reborn, carrying forward not just matter and energy but meaning. It raises questions that border on theology. Are we, in some faint way, the inheritors of a previous universe's legacy? Could our own actions, our own knowledge, someday shape the laws of a cosmos yet unborn? Of course, this is speculative territory. Critics argue that without a mechanism to preserve complex information across a singularity, the idea veers into metaphysics. Yet the math of quantum gravity allows for bizarre possibilities like conformal cyclic cosmology, where the infinite stretch of a dying universe could reset to a new Big Bang, preserving certain patterns in the chaos. Others point to the holographic principle, suggesting the universe's information might compress at the omega point into a seed state for the next cycle. Whether quantum resurrection is science or speculation, it forces us to confront the deepest questions. Is the universe a one-time fluke or part of an endless loop where endings are beginnings? And if consciousness can transcend, what does that make us, passengers on a cosmic ferry, or the architects of realities yet to come? The answers, if they exist, lie in the quantum whispers of a dying universe and the silence that follows. The faint afterglow of the Big Bang, the cosmic microwave background, isn't just a snapshot of the universe's infancy. It's a quantum time capsule etched with whispers from the very first moments of existence. Those subtle temperature variations, mapped in exquisite detail by space telescopes, might hold something even more profound. The tremors of spacetime itself, vibrating at scales so small they blur the line between gravity and quantum mechanics. Imagine listening to a vinyl record of the universe's birth, where the pops and crackles aren't just noise, they're the static of quantum gravity, the universe's primal scream frozen in light. Hidden within those microscopic fluctuations could be evidence that spacetime isn't smooth, but granular, like the pixels on a screen viewed too closely. Quantum gravity theories predict that at the Planck scale, 1 billion times smaller than an atom, spacetime churns with foam like turbulence, a seething ocean of virtual black holes and wormholes flickering in and out of existence. If this foam exists, its ripples would have left imprints on the cosmic microwave background, stretching quantum whispers across the sky as the universe expanded. The pattern we see today, those faint hotter and colder spots, might be magnified quantum jitters, the fingerprint of a reality built on uncertainty. Decoding this signal is like trying to hear a single instrument in a symphony played at the edge of the universe. But scientists are devising ingenious methods to isolate the quantum noise from the cosmic chorus. One approach involves studying the polarization of the microwave background, the direction its light waves vibrate. Quantum gravity might have twisted this polarization in telltale ways, like a prism bending light. Another tactic looks for anomalies in the distribution of hot and cold spots. Classical physics predicts randomness, but quantum gravity could introduce subtle correlations, as if the early universe was stuttering in a language we're just learning to read. The implications stretch far beyond the Big Bang. If quantum gravity's signature is confirmed, it could reveal whether spacetime emerges from something deeper in tangled quantum bits, vibrating strings, or even a cosmic hologram. It might explain why the universe appears so uniform. Quantum fluctuations stretched to cosmic scales during inflation could have sewn the fabric of reality together with invisible threads. And if the noise follows certain patterns, it could hint at extra dimensions, curled up so tightly they only reveal themselves through these primordial tremors. But the greatest revelation might be philosophical. The cosmic microwave background is the oldest light we can see, a messenger from a time before stars, before atoms, before time as we know it had settled into its steady rhythm. If quantum gravity's whispers are there, waiting in the static, it means the universe has been trying to tell us its deepest secret all along. We're not just observers of the cosmos, we're latecomers to a conversation that began 14 billion years ago, listening for echoes of the moment when reality itself flickered into being. We've spent decades scanning the skies for radio waves, laser pulses, any sign that we're not alone in the universe. But what if we've been searching for the wrong thing? What if advanced civilizations aren't broadcasting in clumsy, old-fashioned electromagnetic waves at all, but whispering to each other through the quantum fabric of spacetime itself? Imagine a network of civilizations so sophisticated they've moved beyond radio, using entangled particles to send messages instantly across light years, or encoding data in the quantum states of dark matter. To our primitive detectors, their conversations wouldn't just be silent, they'd be invisible, woven into the background hum of the universe like a secret language written in the static between stars. This isn't just speculation. Quantum communication offers staggering advantages over classical signals. Entangled particles can't be intercepted or jammed, measure one, and its partner instantly reflects the change, no matter the distance. For a civilization spanning galaxies, this would be the ultimate secure network, a cosmic internet immune to eavesdropping or delay. Even more tantalizing, quantum signals don't degrade over distance like radio waves. A single entangled pair could link planets on opposite sides of the Milky Way with perfect fidelity, making our efforts with radio telescopes look like smoke signals in a hurricane. But here's the unsettling twist. If such civilizations exist, their very sophistication might render them undetectable to us. Imagine ants scouring a forest floor for traces of human civilization. They might notice chopped logs or discarded crumbs, but the internet, flowing invisibly through the air as Wi-Fi, would be utterly beyond their comprehension. Similarly, a quantum-based society might saturate the galaxy with communication we simply lack the physics to perceive. Their infrastructure could be right in front of us, neutrinos carrying encrypted data, dark matter particles arranged into celestial servers, and we'd never know. Some scientists argue this could solve the Fermi paradox, the eerie silence of the cosmos despite the high probability of alien life. Advanced civilizations might not be rare, they could be all around us, operating on a quantum frequency we're biologically and technologically blind to. Even their megastructures might defy our expectations. Instead of Dyson spheres harvesting starlight, they could manipulate vacuum energy or entangle black holes for computation, leaving traces only detectable through subtleties in gravitational waves or quantum decoherence patterns. The hunt for these hidden civilizations is already shifting. New generations of telescopes aren't just listening for radio signals, they're probing quantum anomalies in distant star systems, looking for statistical impossibilities in particle behavior that might betray artificial manipulation. Others study neutron stars, whose precise pulses could be subtly altered by quantum communications passing through them. like a flashlight dimming when someone walks between you and the bulb. Even the cosmic microwave background isn't safe from scrutiny. What if its faintest fluctuations aren't random, but a quantum graffiti left by beings who have mastered the art of writing on spacetime itself? The most profound implication isn't that we're alone. It's that we might be surrounded by civilizations so advanced their presence is written in a language we're only beginning to recognize, not in the roar of radio, but in the quiet hum of quantum entanglement, the faintest tremor of a universe where someone or something has learned to speak without making a sound. Quantum mechanics tells us that particles exist in a haze of possibilities, their behavior described by wave functions, mathematical expressions capturing all potential states until measurement forces a choice. But here's the mind-bending leap. What if the entire universe operates under the same rules? Imagine a cosmic scale wave function, a single equation encompassing every particle, every galaxy, every moment in history, all suspended in a superposition of infinite possibilities. In this view, the Big Bang wasn't just the birth of space-time, it was the birth of a quantum probability wave, a flickering blueprint of every reality that could ever exist. At first glance, this seems absurd. We don't experience the universe as a blur of maybes. The sun rises predictably, gravity holds us firmly to the ground, and history feels fixed. But the puzzle lies in the transition from quantum uncertainty to classical certainty. For individual particles, wave function collapse triggered by observation resolves the haze into concrete reality. Scale that up, and the universe's wave function might have undergone its own collapse, winnowing infinite quantum branches down to the single timeline we inhabit. The question is, what or who acted as the observer? One provocative answer comes from the von Neumann-Wigner interpretation. Consciousness itself might be the catalyst. Just as measuring a quantum particle forces it into a definite state, sentient observers could have played a role in solidifying the universe's fog of possibilities into the stable reality we recognize. Think of it like a cosmic game of 20 questions, where every conscious interaction, every glance at a star, every experiment in a lab, nudges the universe toward sharper definition. It's not that the moon isn't there when you aren't looking, it's that the entire cosmos might have needed looking at to fully exist. Critics dismiss this as metaphysical hand-waving, but there's a testable angle. If universal wave function collapse leaves scars, they might be etched into the cosmic microwave background. Tiny anomalies in this ancient light, patterns that defy classical randomness, could hint at moments when probabilities crystallized into facts. Even more tantalizing, if the universe's wave function hasn't fully collapsed, some quantum branches might still linger at the edges of observability. The elusive dark flow, where galaxy clusters mysteriously stream toward an unseen attractor, could be the gravitational tug of a neighboring quantum timeline, a parallel universe just out of reach. The implications rewrite the nature of existence. If the universe has a wave function, then reality isn't a static stage, it's a dynamic process, a constant negotiation between possibility and observation. It suggests that the laws of physics aren't immutable decrees but emergent properties, shaped by the very act of measurement. And if consciousness plays a role, then we're not just passengers in the cosmos. We're participants, co-creators of a reality that's still deciding what it wants to be when it grows up. Black holes have long been considered the ultimate cosmic shredders, monsters that devour matter, light, and even information itself, leaving no trace behind. But what if the opposite is true? What if black holes aren't destructive voids, but the universe's most sophisticated hard drives, encoding every bit of swallowed stardust into the very fabric of their boundaries? This is the startling revelation of quantum black hole entropy, where the event horizon, the point of no return, might be a vast, vibrating ledger, storing data in ways that could finally bridge the chasm between gravity and quantum mechanics. The story begins with a paradox. When matter falls into a black hole, classical physics says it's gone forever. But quantum mechanics insists information can never truly vanish, it can only scramble beyond recognition. Stephen Hawking added fuel to this fire by showing black holes emit radiation and slowly evaporate, raising the nightmare scenario. If a black hole disappears, where does all that swallowed information go? The answer might lie in entropy, a measure of disorder that, for black holes, isn't just random chaos, but a precise quantum fingerprint. Imagine the event horizon as a mosaic made of Planck-sized tiles, each tile a quantum unit of area, humming with microstates we can't yet decode. Just as the air in a room holds hidden information in the motion of its molecules, a black hole's entropy could be a count of all possible configurations of these tiles, each representing a different way the whole could store the data of what fell in. The math is staggering. A stellar mass black hole's entropy is so vast, it dwarfs all the information ever created by humanity multiplied by 1 billion. Yet somehow, this chaos isn't random, it's as precise as a symphony, with every quantum note accounted for. This isn't just theoretical elegance. If black hole entropy is quantum in origin, it suggests spacetime itself might be pixelated at the smallest scales, a grid of interconnected bits rather than a smooth continuum. The holographic principle takes this further, proposing that all the information inside a black hole, the stars, the planets, even the unlucky astronauts, is perfectly mirrored on its two-dimensional surface, like a cosmic DVD encoding a 3D movie. Fall into a black hole, and you're not just crushed into oblivion, you're transformed into a shimmering pattern on its skin, your entire existence rewritten in quantum hieroglyphs. But how do we test this? Clues might come from gravitational waves. When black holes collide, their merged event horizon briefly wobbles like a struck bell, ringing out in frequencies tied to their entropy. Future detectors could analyze these tones, hunting for harmonics that match quantum predictions. Others study Hawking radiation itself, searching for subtle correlations in the particles emitted, echoes of the scrambled information within. Even more radical, if black holes preserve data, then the universe might be doing the same, with every event, every thought, etched into the quantum fabric of spacetime itself. The implications rewrite reality. If black hole entropy is quantum, then thermodynamics isn't just about steam engines and ice melting. It's a cosmic law governing the flow of information itself. It means gravity and quantum mechanics aren't separate languages, but dialects of a deeper code spoken in the whispers of event horizons. And if that's true, then every black hole isn't just a grave for stars. It's a Rosetta Stone waiting to reveal how the universe truly remembers. Dark energy might seem like a distant cosmic curiosity, an invisible force nudging galaxies apart. But what if it's quietly brewing a storm capable of tearing reality apart at the seams? Phantom energy, a hypothetical and terrifying variant of dark energy, doesn't just accelerate the universe's expansion. It grows stronger over time, like a runaway engine with no off switch. If this exists, the fate of the cosmos wouldn't just be cold and empty. It would be violent, chaotic, and perhaps even imminent. Picture spacetime not as a stretchy fabric, but as a sheet of glass under mounting tension. As phantom energy's repulsive force intensifies, that glass would first crack, then shatter, ripping apart galaxies, stars, and eventually atoms themselves in a cataclysm cosmologists call the Big Rip. This doomsday scenario hinges on quantum mechanics in ways that blur the line between salvation and destruction. On one hand, phantom energy could exploit quantum fluctuations in the vacuum of space, those fleeting particle-antiparticle pairs that pop in and out of existence. Normally, these cancel each other out, but under phantom energy's grip, they might stretch and amplify, adding fuel to the cosmic fire. Think of it like a feedback loop in a microphone. Tiny whispers become deafening screeches, accelerating the universe's demise. But here's the twist, those same quantum effects could also offer a backdoor to survival. Some theories suggest that if phantom energy interacts with quantum fields in just the right way, it might trigger a phase transition, a universal reset button that rewrites the laws of physics before the rip becomes inevitable. The timeline for this disaster is as uncertain as it is unsettling. If phantom energy is real, the big rip could be tens of billions of years away or much sooner. It all depends on how quickly its strength grows. Observations of distant supernova and galaxy clusters are already hunting for clues, looking for subtle changes in dark energy's behavior over cosmic history. Even more intriguing are proposed experiments to measure quantum vacuum fluctuations in labs here on Earth, where ultra-sensitive detectors might catch phantom energy's fingerprints in the static of empty space. But the most mind-bending possibility isn't just how the universe might end, it's how we might cheat fate. If phantom energy's destructiveness is tied to quantum mechanics, then so might its undoing. Imagine civilizations of the far future harnessing quantum entanglement to stitch spacetime back together at the last moment, or tunneling into a parallel universe before the rip reaches critical mass. Far-fetched, absolutely. But in a universe where the rules themselves are up for grabs, the difference between doomsday and deliverance might come down to the smallest, quirkiest laws we're only beginning to understand. The universe we see today, glittering with galaxies, swirling with nebulae, might owe its very existence to quantum tremors so minuscule they make atoms look like giants. Picture the cosmos in its infancy, a seething, superheated soup of particles still reeling from the violence of the Big Bang. In that primordial chaos, the tiniest quantum fluctuations, random, ripples in energy at scales a billion times smaller than a proton, could have set the stage for everything we know. Without these microscopic jitters, space might have remained a smooth, featureless void, eternally silent and dark. But thanks to quantum uncertainty, those fluctuations acted like cosmic seeds, places where matter could clump just a fraction denser than its surroundings. Gravity did the rest, amplifying those microscopic differences over billions of years into the galaxies, stars, and planets we call home. Here's the twist: these quantum ripples didn't just shape the universe, they fine-tuned it. The magnitude of those early fluctuations was exquisitely balanced. If they'd been slightly stronger, matter would have clumped too aggressively, collapsing into monstrous black holes before stars could form. Slightly weaker, and gravity would have been too feeble to pull matter together at all, leaving the cosmos a thin, lifeless mist. It's as if the universe rolled a quantum dice and landed on the one number that allowed complexity and life to exist. This precision has led some scientists to wonder, was this luck or something deeper? The evidence for this quantum origin story is etched into the oldest light we can see, the cosmic microwave background. Those faint temperature variations mapped by satellites like Planck aren't random noise. They're the amplified fingerprints of those primordial quantum fluctuations stretched across the sky by cosmic inflation. The pattern matches predictions eerily well. The distribution of hot and cold spots aligns perfectly with what you'd expect if quantum mechanics scribbled the first draft of cosmic structure. Even more compelling, the statistical properties of these fluctuations, their size, spacing, and randomness, mirror the behavior of quantum fields in the lab. It's as if the universe left us a quantum signature, a whisper from its first moment saying, this is where it all began, but the mystery goes deeper. If quantum fluctuations sculpted the cosmos, why do they have the exact amplitude needed for galaxies and ultimately us to exist? One radical answer lies in the multiverse. In an infinite sea of universes, each with different fluctuation strengths, only those with the Goldilocks level of variation, not too hot, not too cold, would give rise to observers. Another possibility is that quantum mechanics itself evolves, with the rules of uncertainty subtly adjusting to favor structure formation. Or perhaps there's an undiscovered principle linking quantum behavior to gravity, a hidden law that tuned the cosmos for complexity from the very first instant. The implications are humbling. Every galaxy, every star, every planet might trace its lineage back to quantum randomness frozen in time. It means the universe isn't just built on uncertainty, it's because of it. And if that's true, then our existence isn't just a happy accident. It's the culmination of a quantum whisper, a ripple in the dark that grew into a symphony of light. At the quantum scale, observing a particle doesn't just measure its state. It can lock it in place like a butterfly pinned under glass. This eerie phenomenon, called the quantum Zeno effect, forces a system to pause its evolution the more frequently it's measured. Now stretch that idea to cosmic dimensions. If conscious observation can freeze a single atom's quantum dance, could the collective gaze of every mind in the universe be quietly holding reality itself in a kind of stasis? It's a thought that blurs the line between physics and philosophy, that the universe isn't just seen but stabilized by its observers, like a cosmic house of cards kept standing because we never stop looking. Take Schrödinger's infamous cat, suspended between life and death until someone peers into the box. In a universe governed by quantum rules, every unobserved system exists in a haze of possibilities. But what if observation doesn't just collapse those possibilities, it actively prevents them from changing? Lab experiments have already demonstrated this with atoms. Bombard them with constant measurements and their decay slows or even stops. Scale that up and the implications are staggering. Galaxies, black holes, even the fabric of spacetime might owe their stability to the cumulative measurement pressure of conscious beings scattered across the cosmos. It's as if reality is a flickering candle and observation is the steady hand shielding it from the wind. But how could something as fragile as human consciousness exert such cosmic influence? The answer might lie in the sheer density of quantum interactions woven into the universe's structure. Every observation, from a scientist in a lab to a bird perceiving sunlight, could contribute to a vast network of quantum pinning, where the act of measurement stitches reality into place. Some theories suggest that complex systems like brains act as entanglement hubs, synchronizing quantum states across vast distances. In this view, the universe isn't just observed into existence, it's maintained by a silent chorus of observers, each glance a thread in the tapestry holding everything together. The evidence for this is speculative but tantalizing. If the quantum Zeno effect operates universally, we might detect anomalies in processes that should decay unpredictably but don't. For instance, the stability of certain radioactive isotopes or even the lifetime of stars could betray subtle signs of cosmic observation pressure. Others propose that the universe's startling uniformity, the way distant regions share nearly identical properties despite never being in causal contact, might reflect a kind of quantum synchronization enforced by early observers in the universe's first moments. Critics argue this veers into anthropic mysticism, but the math doesn't lie. If measurement alters quantum systems and the universe is fundamentally quantum, then observation isn't passive, it's participatory. The most radical implication, reality might not just depend on observers. It might require them, like a play performed for an audience that, by watching, keeps the stage from collapsing. And if that's true, then the greatest mystery isn't why the universe exists, but why it seems to be waiting for us to notice. Empty space is never truly empty. Even in the deepest voids between galaxies, the quantum vacuum seethes with fleeting particles and energies popping in and out of existence. This ceaseless activity isn't just theoretical, it creates tangible forces we can measure right here on Earth. The Casimir effect proves it. Place two uncharged metal plates incredibly close together in a vacuum, and they'll be pushed together by an invisible hand. Why? Because the quantum froth outside the plates exerts more pressure than the limited particle fluctuations trapped between them. It's like subatomic peer pressure, where the weight of the universe's quantum hustle literally moves objects. Now stretch this bizarre phenomenon to cosmic scales. If quantum vacuum energy can nudge metal plates, could it also be pushing galaxies apart? That's the radical hypothesis linking the Casimir effect to dark energy, the mysterious force accelerating the universe's expansion. Imagine the entire cosmos as a pair of plates separated not by micrometers, but by billions of light years. The quantum vacuum between them might generate a repulsive pressure strong enough to overcome gravity's pull, explaining why the universe isn't just expanding, but doing so faster and faster. It's as if space-time itself is an ocean with an undercurrent we've only just begun to sense, but there's a glaring puzzle. Calculations show the vacuum energy predicted by quantum field theory is a staggering 10 to the power of 120 times stronger than what we observe in dark energy. That's like expecting a hurricane and feeling only a breeze. Some physicists argue this discrepancy hints at unknown physics. Perhaps vacuum energy isn't uniform, but varies in strength across dimensions we can't perceive. Others propose that most vacuum energy cancels itself out through symmetries we haven't discovered, leaving behind just the faint residue we measure as dark energy. It's like trying to hear one instrument in an orchestra playing at full volume while the rest are perfectly muted. The search for answers is turning to some of the most precise experiments ever devised. Advanced versions of the Casimir setup, using nanostructured materials and cryogenic temperatures, are hunting for anomalies in vacuum energy that might mirror dark energy's behavior. Meanwhile, astronomers study the large-scale structure of the universe, looking for patterns in galaxy distribution that could betray vacuum energy's fingerprint. Even gravitational wave detectors might help. If spacetime foam exists at quantum scales, ripples passing through it could carry subtle distortions akin to light shimmering through heat haze. The implications rewrite our understanding of nothingness. If dark energy stems from quantum vacuum fluctuations, then the emptiest regions of space are secretly the most active, humming with energies that shape the fate of the cosmos. It means the universe isn't just expanding, it's being stretched from within, propelled by the restless whisper of particles we can't even see. And if that's true, then the greatest force in the universe might not be gravity or light, but the ghostly pressure of the void itself. Time loops aren't just science fiction, they might be written into the fundamental laws of quantum physics. Imagine a single particle, not just moving forward in time, but bending its own history like a snake eating its tail. This is the mind-shattering premise of retrocausality, where quantum events ripple both forward and backward through time, creating self-contained loops of cause and effect. At the microscopic scale, particles can appear to decide their properties after they've been measured, as if the present reaches back to tweak the past. Now stretch this logic to cosmic scales. What if the universe's relentless expansion isn't just a one-way street, but our ouroboros of creation, a cycle where the future breathes life into its own beginning? Take the quantum delayed choice experiment, where photons seem to choose whether they behaved as particles or waves after they've already passed through a detector. It's as if the particle's past changes based on decisions made in its future. Now apply that to cosmology. The Big Bang's initial conditions, the precise balance of matter, energy, and expansion rate, were so improbably fine-tuned that even slight variations would have left the universe a lifeless void. Coincidence, or could those conditions have been subtly adjusted by observers billions of years later, their very existence looping back to ensure the universe had the right recipe for complexity? This isn't just philosophical hand-waving. The math of quantum gravity allows for closed time-like curves paths through spacetime that return to their starting point, like a Möbius strip woven from causality itself. In these models, dark energy's acceleration could be more than just cosmic repulsion. It might be the universe's way of feeding its own birth, with expansion fueling the quantum fluctuations that seeded galaxies, which in turn gave rise to observers whose quantum measurements stabilized the initial conditions needed for, well, everything. A cosmic bootstrap paradox where the effect becomes its own cause. The implications dismantle our most basic assumptions. If causality can loop, then free will and determinism might not be opposites, but partners in a dance where choices in the present sculpt the past just as the past shapes the future. It suggests that time isn't a river flowing in one direction, but an intricate feedback system with every observation, every measurement, subtly rewriting the universe's code at the deepest level. And if that's true, then the expansion of space isn't just something that happens to the cosmos. It might be the universe remembering how to begin. The silence of the cosmos is deafening. With billions of galaxies, each harboring countless stars and planets, the universe should be teeming with civilizations, yet we've found no trace. The Fermi paradox has haunted scientists for decades. But what if the answer lies not in biology or engineering, but in the quantum fabric of reality itself? Imagine a universe where advanced civilizations aren't hiding or extinct, they're trapped in a quantum superposition, existing in states we can't perceive or interact with. One radical explanation revolves around quantum decoherence, the process that collapses fragile quantum states into the classical reality we recognize. For interstellar communication, most searchers assume aliens use electromagnetic waves like radio or lasers. But what if they've moved beyond this, encoding messages in quantum entangled particles or manipulating spacetime itself? The problem: quantum systems are notoriously delicate. The moment an entangled signal encounters cosmic dust, radiation, or even the gravitational warping of interstellar space, it decoheres, crumbling into noise before reaching us. It's like trying to whisper across a hurricane. The message might exist, but the universe itself scrambles it beyond recognition. Even wilder is the idea that advanced civilizations could exist in macroscopic superpositions, their very reality undetectable to our classical instruments. In the quantum world, particles can be in multiple states until observed. Scale that up, and entire societies might thrive in parallel configurations, their planets and technologies smeared across probability space. To them, our universe could appear just as ghostly, a shadow they can't touch or measure. This wouldn't just explain the silence, it would mean we're not alone, but separated by a barrier more fundamental than distance, the quantum classical divide. The implications rewrite the rules of the search for extraterrestrial intelligence. Instead of scanning for radio signals, we might need quantum telescopes, instruments sensitive to entanglement or superposition in cosmic structures. Some theorists propose looking for anomalies in the cosmic microwave background, where quantum-locked civilizations could leave statistical fingerprints. Others suggest that dark matter's elusive nature might hide more than particles. It could be the substrate for entirely quantum-based life, thriving in a realm where our physics barely applies. But the most haunting possibility is this: if quantum mechanics prevents civilizations from detecting one another, the universe might be a gallery of ghosts, each convinced it's alone. Not by distance, not by time, but by the very laws that govern reality. And if that's true, then the answer to the Fermi paradox isn't that no one is out there. It's that we're all prisoners of the quantum, shouting into a void that can't shout back. The Big Bang should have been messy, a chaotic explosion sending matter flying in all directions, only to collapse back under gravity's crushing grip. Instead, the universe did something inexplicable. It inflated faster than light, stretching from smaller than an atom to the size of a grapefruit in a fraction of a second. This hyper-fast expansion, known as cosmic inflation, smoothed the cosmos into the eerily uniform universe we see today. But what fueled this runaway growth? The answer might lie where Einstein's relativity and quantum mechanics collide, a theory of quantum gravity so radical it could rewrite the first chapter of cosmic history. Picture gravity not as a relentless force, but as a flickering quantum shadow. At the tiniest scales, where particles pop in and out of existence, gravity might operate in reverse, repelling rather than attracting. This isn't just speculation. Some quantum gravity models predict that in the extreme conditions of the early universe, gravitational interactions could have briefly switched polarity, turning spacetime into a cosmic trampoline that launched the universe into hyperdrive. Imagine a rubber band suddenly snapping not inward but outward with explosive force. That's the kind of quantum anomaly that might have kick-started inflation, transforming a sluggish expansion into a runaway sprint. The smoking gun for this theory could be hidden in gravitational waves, ripples in spacetime left over from the universe's violent birth. If inflation was driven by quantum gravity, those waves should carry a distinct chaotic signature, like the static of a radio tuned between stations. Current detectors like LIGO aren't sensitive enough to catch these primordial whispers, but next-generation observatories, such as the proposed Big Bang Observer, could sift through the cosmic noise for traces of quantum gravity's fingerprints. Even more tantalizing, if quantum fluctuations in gravity seeded inflation, they might also explain why the universe is so finely balanced. The same randomness that birthed galaxies could have fine-tuned the cosmos for life without any cosmic designer. Just quantum probability playing out on the grandest stage. Yet the implications go deeper than the Big Bang. If gravity's quantum behavior fueled inflation, it might also hold the key to dark energy, the mysterious force accelerating the universe's expansion today. Just as repulsive gravity could have stretched spacetime in the past, lingering quantum effects might still be tweaking the cosmos, nudging galaxies apart like an invisible hand. It's a spine-tingling possibility that the universe's birth and its ultimate fate are bookends of the same quantum gravity story, written in a language we're only beginning to decipher. The missing piece, a unified theory stitching gravity to the quantum world. String theory, loop quantum gravity, and other candidates all offer glimpses, but none yet deliver the full picture. Until they do, the inflationary epoch remains a puzzle, one where the answers might not lie in the cosmos we see, but in the quantum shadows we're still learning to measure. And if we ever crack that code, we won't just understand how the universe began. We'll finally see gravity for what it truly is, not just the architect of galaxies, but the phantom hand that shaped existence itself. If our universe is a simulation, quantum mechanics might be its source code, and like any complex program, it could have bugs, those strange, unpredictable behaviors we chalk up to quantum randomness. They might not be flaws in nature, but glitches in the system, tiny fractures where the simulation shows its seams. Think of a video game where textures flicker when the graphics card struggles, or non-playable characters clip through walls when the physics engine stutters. Now imagine those same artifacts happening at the subatomic level, where particles teleport through barriers, exist in two places at once, or change behavior simply because we're watching. These aren't just scientific curiosities, they could be cosmic debug logs waiting to be decoded. Hunting these anomalies isn't science fiction. Labs worldwide are already catching quantum behavior that defies classical logic. Take tunneling, where particles phase through solid barriers as if they're ghosts. In a simulation, this could be a rendering shortcut, like a game simplifying calculations by letting a character pass through a wall if the player isn't looking closely. Or consider entanglement, where particles sink instantly across light years, breaking Einstein's speed limit. In a programmed reality, that's not magic. It's lazy coding, a developer reusing the same variable in two places to save processing power. Even wave function collapse, where observation forces particles to pick a state, mirrors how video games only render what the player sees, leaving distant terrain fuzzy until observed. The real test, finding patterns in the chaos. True randomness is messy, but simulated randomness often has statistical tells, subtle repetitions or biases buried in the noise. Some physicists are scouring quantum noise for these fingerprints, using ultra-precise measurements of particle decay or entanglement to spot irregularities. Others propose more radical experiments, like deliberately stressing the simulation's hardware with massive quantum computations, hoping to trigger a telltale crash, or at least a frame rate drop in the fabric of reality. But here's the twist. If we're in a simulation, the programmers might have anticipated this curiosity. Quantum encryption could be their way of locking the universe's admin privileges, ensuring we never peek behind the curtain. Or worse, what if finding a glitch triggers a patch? The greatest cosmic irony might be discovering the truth, only to wake up the next day in a universe where the anomaly no longer exists, silently fixed by unseen hands. Whether bug or feature, these quantum quirks don't just challenge our understanding of reality. They invite us to question whether the universe plays by rules, or if the rules themselves are just someone else's code. Quantum cosmology doesn't just rearrange equations, it shatters our deepest intuitions about existence. At the intersection of quantum physics and cosmic expansion lies a philosophical vortex where the very nature of reality is up for grabs. Is the universe a fundamental entity, solid and independent, or is it something far stranger, an emergent mirage conjured into being by underlying rules we barely comprehend? Consider the holographic principle, which suggests our three-dimensional world might be a projection from a two-dimensional surface at the edge of spacetime. It's as if everything we see, every galaxy, every thought, every breath is just a shadow cast by information encoded on some distant cosmic boundary. This isn't just science, it's a radical reimagining of what real even means. The implications ripple through metaphysics like a tidal wave. If reality is emergent, then time and space aren't foundational. They're approximations, useful fictions that emerge from something far more abstract. Think of a whirlpool in a river. The vortex feels like a distinct object, but it's really just water moving in a particular way. Similarly, our experience of a continuous, flowing universe might be a side effect of quantum entanglement, with every particle's connection to every other weaving the illusion of spacetime. Some theories go further, proposing that consciousness itself plays a role in crystallizing reality from quantum potential. In this view, the universe isn't just observed, it's participated into being, a collaborative artwork where every glance, every measurement adds another brushstroke. Yet the most unsettling possibility is that reality might be fundamentally illusory. Quantum mechanics already blurs the line between observer and observed, but cosmic expansion adds another layer. As the universe accelerates, regions of space are disappearing beyond our event horizon, their light forever too distant to reach us. This raises a chilling question. If parts of the universe are permanently inaccessible, can we ever claim to know the whole? It's like trying to map a room while blindfolded, knowing that unseen walls keep receding faster than you can grope toward them. The philosopher in us whispers, if reality is what we can interact with, then the universe isn't just expanding, it's dissolving, taking with it any hope of an objective, independent existence. Amid these dizzying ideas, one thread remains taut: the interplay between the infinitely small and the cosmically vast. Quantum fluctuations in the early universe, magnified by inflation, birthed galaxies. Now, those same galaxies flee from us, their retreat governed by dark energy, which might itself be a quantum phenomenon. The cosmos seems to be telling us that the rules of the very small don't just apply to atoms, they built the heavens. This isn't just physics, it's a new mythos, a story where the universe isn't a cold machine, but a dynamic, evolving entity with quantum uncertainty woven into its bones. And if that's true, then the greatest mystery isn't how the universe works, but what it's becoming and whether our tiny human minds can ever truly grasp the unfolding. From the spooky whispers of entangled particles bridging cosmic distances to the dizzying possibility that our universe could be a simulation running on quantum code, these 35 theories don't just push the boundaries of science, they shatter them entirely. What began as a journey through the quirks of quantum mechanics has spiraled into something far grander, a revelation that reality, as we know it, might be the tip of an iceberg lurking in dimensions we can't yet perceive. Whether it's black holes encoding information like cosmic hard drives or dark energy emerging from the froth of spacetime itself, each theory whispers a tantalizing secret: that the universe is far weirder, far more interconnected, and far more alive with mystery than we ever dared to dream. So where does that leave us, staring up at the night sky with fresh eyes perhaps? The same stars that guided ancient navigators now hint at wormholes, holograms, and timelines folded like origami. Science fiction once painted these ideas as fantasy, but today they're the cutting edge of physics, debated in labs and lecture halls with equations to back them up. That's the real magic here, not that these theories exist, but that they're testable. The cosmic microwave background could hide echoes of parallel universes. Gravitational waves might carry traces of quantum foam. Every unanswered question is an invitation not just to wonder, but to explore. But here's the most thrilling part: this isn't the end, it's a checkpoint. For every theory we've unraveled, a dozen more wait in the shadows, daring us to look deeper. Maybe you're drawn to the elegance of entanglement weaving the cosmos together, or perhaps the chilling simplicity of the simulation hypothesis grips you. Whatever resonates, one thing's certain: the universe isn't just a story to observe. It's a conversation, one where your curiosity fuels the next chapter. So hit pause, rewind, or dive into the comments below. Which of these ideas rewired your brain, which kept you up at night? Let's keep the debate alive. And if today's journey left you hungry for more, don't forget to subscribe, because the next revelation might be just a quantum leap away. The cosmos never stops surprising us. The only question is, are you ready for what's next?